we compare model simulations and observations, and by doing so we can see how well climate models capture historic changes in the system. So if they're doing a good job, then we have more confidence in their projections, but if they're doing a bad job, then we have less confidence in their projections. So I'm going to talk about this comparison. And finally, the fact that we have an anthropogenic forcing for several decades now, it's kind of perturb the system and resulting in the kind of different physical phenomena that pop up. And it allows us to kind of better understand the physics of the system when they have this kind of very strong forcing in recent decades. Okay, so I'm going to focus on the tropical circulation. And I'm showing you, this is a snapshot from a video from the Met Office that's to illustrate the tropical circulation. So there are different circulation types in the tropics, and the Hades circulation is one of them, is the main kind. What you see here is Earth, and those bubbles are basically a cross-section of the atmosphere, okay? And the arrows show you how the air flow within the atmosphere, okay? And you can see that the air is rising around the equator. It goes up in the atmosphere, and when it reaches the upper bound of the troposphere, it goes polewards in both hemispheres. Then it descends back to the surface in the subtropics around latitudes 20 to 30, and then it returns back to the equator at the surface. Okay, this is the Hades circulation. You have two cells, one in the northern hemisphere and one in the southern hemisphere. Okay, and these cells have a large impact on our climate, and I want to show you one example of that, which is
אני לא שומע.
לא שומעים כלום.
okay. So on the left, you see the distribution of precipitation in blue. This is taken from Hartmann's book. It's average over recent decades, and you can see the distribution of precipitation as a function of latitude. And red is surface evaporation, and the difference in purple is precipitation minus evaporation, what we call net precipitation. And you can see that it's positive around the equator, where we have this ascending branch of the circulation, and it results in heavy precipitation, but it's negative in the subtropical regions, where the air descends back to the surface and basically suppresses precipitation. So from that, you can see what I'm trying to tell you is that it has a large impact, for example, on the distribution of precipitation, but also I can show you similar plots for humidity or temperature and so on. So it carries a lot of heat and moisture in this kind of circulation. This is why it's very important for us to understand how anthropogenic emissions have been and will affect the intensity or changes in this circulation. Right? Right. So to examine the circulation, we need some mathematical framework to do it, and we use basically it's called a mass stream function. You basically take the meridional wind in the atmosphere. Okay, think about those winds that travel from the equator towards the pole in the circulation. And you take an average over all longitudes, and you take a vertical integral of that. You get, this is the definition of the stream function, and it looks like that. So again, it's taken from Hartmann's book. You see here how the stream function looks like in pressure, so in height and latitude space. And you can see the two cells, the two Hades circulation, one in the northern hemisphere in red and one in the southern hemisphere in blue, the same cells that you saw before. Okay, this is just a mathematical representation of the picture that you saw before. And to measure how the intensity of this cell is changing, we're going to focus on the maximum value of each one of these cells. Okay, so let's see what models are doing. So on the right, you see the evolution of the intensity of these cells. So this psi max is the intensity of the cell, how fast these are rotating, okay, with time over the 20th and 21st century. This is taken from climate models. So you take a climate model, you run it over the 20th and 21st century, and you calculate this thing, you take the maximum value and you just plot it with time. Okay, this is the northern hemisphere cell, and in the upper part is in the lower part is the southern hemisphere cell. Okay, and the black line is the mean of the model, and the gray is some uncertainty across the models. And what I want you to take from here is that in the northern hemisphere, the circulation is projected to weaken by the end of the century, right? You see the negative values. We expect to see a reduction of approximately 16% by the end of the century, but not in the southern hemisphere. So we're going to focus on the northern hemisphere, and first we're going to ask whether this weakening that we see in models is already occurred in observations, okay, in recent decades. We want to see whether we can already find the anthropogenic signal in recent decades. Okay, now the issue is that this is not an easy task to do because currently we don't have any observed wind record in the atmosphere that is continuous in time and space that would have allowed us to estimate the stream function. There's no wind record in the atmosphere.
Can you say something about the mechanisms that causes it, or I mean, why do we see this decrease?
I will get to it by the end of the talk, okay? So that I would not tell you why, but it's related to there's a lot of asymmetries between the northern and southern hemisphere regarding the response to anthropogenic emissions. And it's related to the fact that you have more mass land in the northern hemisphere related to the southern hemisphere, and the ocean play a critical part in doing these asymmetries. And specifically for the strength of the circulation, it's a combination of what ocean circulation is doing, because ocean can transport heat between the two hemispheres, right, across the equator. But the atmosphere is not. The atmosphere is really symmetric across the equator. So the ocean heat transport playing a critical role in causing these asymmetries. And on top of that, the amount of latent heat and sensible heat release that you get from the ocean in the southern hemisphere is much larger than what the land parts are doing here. So this is another component of, but it's all coming from the ocean. I can show you later some plots about why you have this asymmetry.
It's not that there's more anthropogenic activity in the northern hemisphere, it's just the ocean basins.
Yeah, because anthropogenic activity, putting aside aerosol injections, if you talk about greenhouse gas emission, they are well mixed in the atmosphere. So you can emit it in China, and then in 1 year, it's already homogeneously spread out across the entire globe. So it doesn't really matter who emits greenhouse gases. So you can have, for example, the Western countries reducing their emissions in recent decades, but they are moving their entire industry to import that from from East Asia. So it doesn't mean that we are now emitting less. We're just emitting from different places more, but it's spread out so quickly, so it doesn't really matter. But when it comes to aerosol injections, you're right, that would be a difference. So you have a lot of aerosol injections in different parts in the northern hemisphere, but not so much in the southern hemisphere, and then you can see a signal that is more related to this. Okay, so the fact that we don't have a wind record is related to the point that I started with, that we have a large uncertainty in how the flow has changed, because we basically don't know how the winds behaved in recent decades, and it prevents us from assessing, for example, what's the role of human activity, and most importantly, we don't know how much can we trust climate models, giving us projections for the future, how the circulation will change in the future, how the precipitation is going to change in the future, given that the circulation is highly affecting precipitation. So we don't have observed wind record, but we do have a lot of observation at the surface. We have good observation of, for example, surface temperature, surface pressure, and so on. So what we want to do next is we want to derive the mathematical relationship between the strength of the circulation, so how fast this is rotating, to some surface variable that we have observation of, and use it as a proxy for the strength of the circulation. Use it to constrain the strength of the circulation and get an idea of how the circulation have changed using that proxy. Okay, that's the general idea. So I'm not going to go through the mathematical derivation. It's not that interesting, but I just want to give you where we are starting and where we end. So you start from the Navier-Stokes equation. You take the momentum equation, which describes how an air parcel moves in the atmosphere, all the forces that act on an air parcel in the atmosphere. You do some algebra, which I'm not going to go into, and we got to this relationship that the strength of the circulation on the left-hand side, this side here, so again, how fast this is rotating, should be linearly related to the meridional gradient of sea level pressure, okay? And there are available measurements of sea level pressure. So if this relationship that we derived actually holds, then we can use measurements of sea level pressure, calculate this function on the right-hand side, and use it as a proxy to constrain the left-hand side and say how the circulation has changed in recent decades. Okay, that's the idea of what we want to do. Okay, so first we can verify this, for example, using climate models where we have both sides of the equation. So let's do that.
Can I ask a
Yeah.
question about sea level pressure? So you should use the open sea one instead of the coastal water.
Sorry?
It should use the open sea
Yeah.
instead of the coastal water because coastal water a lot of effect from the land, so
Yeah.
sea level pressure is not only changing.
That's right. We use open ocean sea level pressure. So we did several things. I'm going to show you one of the results of the observation that we use. So you can use also surface pressure with some additional assumption to this equation. But I'm going to show you the result of what you mentioned, which is open sea level pressure from ships. It takes mostly from ships and stuff.
Thank you. What is that?
F is the Coriolis parameter here. But that's a constant, so it's not really. Okay, so we go to models. So on the plot here, you see in black line the evolution of the strength of the circulation that you saw before. It corresponds to the left y-axis, and you see the reduction over the 20th and 21st century, and you see this weakening that we saw before, the same plot you saw before in the beginning of the Halley circulation. Models show this weakening in recent and coming decades, and this is the average over all models together. The red line corresponds to the right y-axis, is this function that we derived of the meridional gradient of sea level pressure. And you can see that in the models, at least, not only that it overall nicely captures the weakening that we see by the end of the century, but also the year-to-year variation that we have on the circulation. And this holds not only in the multi-model mean, but also we can see that across models. So, and to see that, I'm showing you on the right, this is the historic changes. Basically, we do a linear regression of these two metrics over that period, 1960 to 2014. The y-axis is the historic trends or changes in the Halley strength, and the x-axis is the historic trends in the function that we derived of sea level pressure. Okay, across different models. So each dot here is a different climate model. And you can see there is a nice linear relationship between the two, which we could have predicted from the derivation that we did. We expect some linear relationship between the two, and we got something similar. Great. So now we can add our assessment from observation to the x-axis. We can take measurements of sea level pressure, calculate those trends, these changes over recent decades, and add some assessment to the x-axis. Okay, so that would be the blue line. We use here a data set called ICOEDS, which basically collects millions of sea level pressure measurements per year, mostly from ships. It also uses buoys, stuff like that. We also use another data set, which also take measurements over land, but I'm not going to show you that because the results are pretty much similar, because the Halley circulation is mostly concentrated over ocean. So even if you add some things over land, it doesn't really matter. So the blue line here is the observed changes. So again, we take the observation, we calculate this function, we calculate its trends, and this is the vertical blue line with some uncertainty in shading.
What do you mean? Why is it a change?
Because we do a linear regression over time. So it's how much this change per year. It's this function per year.
Per year. Okay.
It's the trend of this function. Okay. Right. So we're going to do what we call emergent constraint analysis. We're going to exploit the strong linear relationship that we have between those two variables that comes from the momentum equation. It has a physical meaning. We didn't get it by a fluke. It has a strong physical meaning. Together with observed trend, we can put a constraint on the y-axis, which would be this horizontal black line, which tells us that the circulation has been weakening. You can see by the negative value, right? So just a weakening of the circulation in recent decades, consistent with what we see with most of the models. This is the uncertainty. It has a large uncertainty, but still suggesting a reduction in the circulation in recent decades. So what we want to ask next is, can we attribute this weakening to anthropogenic emissions, right? Not any change that we see in the system has to be related to human activity. We have natural changes in the system. Solar flux could change, volcanic eruptions, and also there is internal noise in this kind of chaotic system. So not necessarily any change that we see in the system has to be due to human activity.
But Christian, this is over. How long is the period?
This is 55 years.
I see now. No, I see that. I didn't see that.
So we start, this is when the data is available. It starts in 1960 and it ends in 2004. Okay, so to attribute a given signal in the system, we're going to use what we call an attribution analysis, and specifically we take a fractional attributional risks approach, or in short, FAR. And this approach is illustrated in this schematic here. So imagine that the red PDF is the distribution of the circulation trends in recent decades across the models. Okay, so if you calculate in each model how the circulation has changed, and then you put it in a PDF, that's the red PDF. And the vertical black line will be the observed trend. Okay, so the red hatching tells us the probability of exceeding the observed trend across the models, basically. Okay? The green PDF is also a distribution of the trends in recent decades across models, but this time you run the models without anthropogenic emission. You just turn it off, right? It's easy to do it in the model. It's hard to do it in reality. But in model, we just can turn off anthropogenic emission. So you do that. So the green hatching here will tell you the probability of exceeding the observed trend in a world without anthropogenic emission, only with natural forcing agents, right? Natural forcing agents, again, meaning we just include changes in solar fluxes, volcanic eruptions, natural changes in the chemistry in the atmosphere, and so on. So the ratio between the red and green will tell you by how much anthropogenic emission increase the probability of exceeding the observed trend. And 1 minus this ratio is the definition of FAR. So when FAR is equal 1, there is 100% chance that we can attribute a given signal to anthropogenic emission. When it equals 0, there is 0% chance that we can. Okay, that's the idea of FAR. Okay, so now we go back to our derived Hadisal trends. So it starts from 1960. So we take those trends, those linear regressions since 1960 up to any given year. And for each length of trend, we compare it to a distribution of simulation with and without anthropogenic emission. So we calculate this FAR value for each period of trend, from 1960 up to 1970, up to 1979, up to, and so on and so on and so on, up to present. So you're going to see an evolution of this FAR metric. So you see how FAR develops with time. And you can see that at first it's increasing with time, meaning there is a larger role of human activity to work in the circulation. And by the early 2000s, it's already exceeded a value of 0.99, meaning that we have very high confidence of more than 99% chance that human activity weaken the circulation. And, or in other words, as we said before, human activity increased the probability of seeing such a trend by a factor of 100 over this period. Okay, so we're able to attribute this with high confidence to anthropogenic emission. Cool. So now that we know that anthropogenic emissions have been weakening the circulation, can we use this knowledge of how sensitive the circulation is to anthropogenic emission to also constrain model projections, right? You saw that in the future also models suggest a weakening due to increasing greenhouse gases. So can we use our knowledge of how sensitive the system is in recent decades to put some constraint on model projections? And the answer is yes, but only up to some extent. So in this figure, the y-axis, you see the future changes in the strength of the circulation. So you basically take the strength of the circulation in the end of the 21st century and in the end of the 20th century, and you take the difference between the two. Okay? And it is plotted against the historic changes in the flow. Okay, across different models. So each dot here is a different model. And you can see, as we saw before, that most models show a reduction, a weakening of the circulation by the end of the century. On the y-axis, you see most of them show negative values. Okay, this is how much the circulation is going to weaken by the end of the century. Just the difference between the late 21st and late 20th century in the strength of the circulation. And the green PDF basically show you how these dots are distributed along the y-axis. The height of the PDF is meaningless. Okay, it's just for illustration. Is that clear? Is the figure clear?
Mm-hmm.
Yeah, okay. So now we're going to do another emergent constraint. We're going to add our estimate of how much the circulation have changed to date from the sea level pressure measurements that we found. We're going to add it here and get a constraint on the y-axis on how much the circulation is expected to change by the end of the century. So the black PDF is what we found before, how much the circulation have changed to date from the sea level pressure measurements. And together with this linear relationship, it yields the purple PDF. It suggests a larger weakening by 80% more larger weakening relative to the current prediction. So current prediction would be the green PDF, but the emergent constraint suggests actually a larger weakening of the flow. That would be the purple PDF. So we expect a larger weakening of the circulation relative to current predictions by the end of the century. So finally, I want to ask, what would be the climate impacts of a stronger weakening of the flow? We saw before that it has a huge impact on precipitation. So can we say something about precipitation predictions if we know that the circulation is expected to undergo a larger weakening? And to answer that, first I want to show you the future changes in precipitation. So this is, again, our precipitation is projected to change across latitudes in the northern hemisphere. Again, difference between the late 21st and late 20th century based on model simulation. Okay? So the black line is the mean of the model, and you can see positive values. It suggests an increase in precipitation throughout the tropics and subtropics. Okay? So to understand what's the role of the circulation, we're going to use what we call the moisture budget equation. The moisture budget, for those of you who are not familiar, basically you take it suggests that the precipitation minus evaporation at the surface is balanced by how much convergence of moisture we have in the atmosphere. So basically, if you converge moisture, right, from mass continuity, if you converge moisture, it condenses and becomes precipitation. If you diverge the moisture in the atmosphere, you need to have evaporation, basically. Okay? That's the idea behind this equation. So this equation tells us that the future changes here denoted by delta, the future changes in precipitation should be balanced by future changes in this moisture flux convergence. And you can decompose this to what the circulation, this V here, is doing. That will be that, Q delta V, or what just increasing specific humidity in the atmosphere, or for example, evaporation. So let's add the contribution of what we are after, which is the circulation part. That will be the red line here. And you can see that the circulation acts to reduce precipitation in the deep tropics and increase it in the subtropics. And this is what we expect if how the circulation would weaken, because it would act to less result in precipitation in the ascending branch here, right? If this entire thing going to weaken, we have less precipitation here, and it would act to less suppress or increase precipitation in the subtropics. So it's doing the opposite of what it's trying to do here, because we are weakening the circulation, basically. So we have less precipitation in the deep tropics, but more precipitation in the subtropics, because it would act to less suppress the heat, the air here, and thus we're going to have more.
The integral of these two curves needs to be the same, right?
The integral with latitude?
Yes.
No, because you have the other components.
Okay.
I'm not going to go into.
Okay.
Right. So this might suggest that this increase that we see in the subtropics of precipitation in black might come from the weakening of the circulation. Okay, that's to increase it. And indeed, we find a similar linear relationship in the models. On the y-axis is the future changes in precipitation in the subtropics, so this black line, basically, plotted against the future changes in the atmospheric circulation. Okay, again, the difference between the late 21st and late 20th centuries across models. So each blue dot is a different model. And you can see there's a nice linear relationship that we'd expect from this kind of equation, this simple kind of exercise. And again, the black PDF shows you how these dots are distributed along the y-axis. And we're going to do a final emergent constraint. We're going to put on the x-axis our assessment of the stronger weakening of the flow that we found, right? The 80% larger weakening of the flow that we found. That will be the purple PDF. And together with that linear relationship, it gives us the red PDF, which tells us that we expect to see more than a doubling of subtropical precipitation increase relative to current predictions.
Over C.
Sorry, this is not over C. This is, so the precipitation here is zonally average over all longitudes, but we also decompose it to the different regions, and you can mostly see it over the Pacific, North Africa, and South Asia. Over the Atlantic, you don't see it mostly because the Halley circulation is not really weakening over that region. Okay. Right. So I'm going to just the last part, and this was done with one of my PhD students, Hess. The question we'd like to address here, so we saw that human emissions have been weakening the flow, and we saw the consequences for model projections, and now we want to understand how unprecedented are these changes compared to what natural forcing agents did before the industrial era, okay, over the last millennium, for example, where we have no human emissions. And I'm plotting here this famous hockey stick figure by Michael Mann, where you see here the surface northern hemisphere temperature. This is from reconstructions and observations since the year 1000 up to 2000, and we can see this cooling trend, right, that lead to the Little Ice Age over the last millennium. And then since the pre-industrial area, we have this increase, this warming, right, unprecedented warming that we see in recent decades up to today. So we want to create the same thing for the Hadith circulation strength. Okay. Now the issue is that we don't have an observed wind record, right? We don't have one for the last decade, so for sure we don't have one going back centuries. But there is a very good reconstructions of the forcing agents that drive the system, right? We have very good reconstruction of solar fluxes and volcanic eruptions and CO2 emissions. We know all of that from reconstructions, so we can use those basically just to integrate our models. Our models only solve the primitive equation of physics in the atmosphere and ocean and so on. They just need the correct forcing agents in order to get the correct climate. So what you want to do here is you want to take all of these reconstruction of forcing agents, plug them to the models, and let the models simulate how the climate looked like in past centuries. And then from that, we can calculate how the circulation looked like. Now so you can do that. It's very heavy computationally to do it because we cannot use just one simulation, because the system is so sensitive, it's a chaotic system. So because it's so sensitive to the initial conditions, one simulation, if we analyze a specific change, could be just due to some internal noise in the system. It not necessarily have to be due to response to some external forcing that we put in. So to overcome that, we run an ensemble of simulation, but we change the initial condition, for example, of the temperature in the atmosphere by 10 to the minus 14. And we run like 10 members of those, or 100 members, how much we'd like to run. But each one of those simulations are subjected to the same external forcing, but it differs by the 10 to the minus 14 Kelvin in the initial condition. And this leads to different time evolution. And if you have an ensemble, we can average all of these members and get rid of this sensitivity dependence to the initial conditions. And we only look at the response to those external forces. Is that clear? Okay. So we do that. And this is an extended evolution of the Hadith strength, starting from 8050 to the end of the century. Before you just saw this part, the weakening of the circulation, and now I'm extending it back in time. And you can see that the circulation has been very slightly increases over the pre-industrial area in the last millennium before anthropogenic emissions started, and eventually we got this very strong weakening. So what you want to understand here, and in the last minute, I just want to try to give you some intuition on why natural forcing agent slightly intensify the flow versus why anthropogenic emissions strongly weakening. Okay. Okay, so to do that, what Orr did, she analyzed an elliptic equation for the stream function, for the strength of the circulation. I'm not going to go into how do you derive that. It's not really important, but you can see there are different components that affect the strength of the flow. So the operator on the left-hand side, you have, for example, Earth rotation rate is F. You have S square, which is the static stability. It's tells you something about the vertical structure of temperature. And on the right-hand side, you have components like diabatic heating in the atmosphere, heat and momentum fluxes in the atmosphere, or surface friction. So took all of those outputs from the models, solved this equation, and she got a solution for psi, for the strength of the circulation. And if the solution adequately capture how the circulation behaves in last centuries and in coming decades, then we can use this equation to ask via which processes natural forcing agents strengthen the flow, but human activity weakens the flow. Okay? That's the idea. So we verify this equation. Here you see the time evolution, again, of our strength of the circulation over the 20th and 21st century. The black is what you saw before, calculating it from the stream function with the meridian velocity, and the blue is the solution for this equation. You can see that it does a really nice job capturing the overall weakening, for example, in recent and coming decades. So it gives us confidence to use this equation and better understand the contribution of each one of these components to this weakening or to the strengthening in past centuries. So we do that. This is the contribution of each one of the components in the equation to the weakening over the 21st century and the classification in the last millennium. And I want you to look at two things. So for example, the weakening, and this is related to what you asked, is mostly driven by changes in the vertical temperature structure. You can see this red line here, this S square. The intensification by natural agents is due to two terms. One is related to diabatic heating, and the other is also this S square. So it seems that human activity in natural agents have opposite effects on the circulation, partially by having opposite effect on the vertical temperature structure, okay? So I would like just to give you an intuition of why human activity is changing the vertical temperature structure in such that it causes a weakening, but natural forcing agent changing the temperature structure such that it causes an intensification. And I want you to look at this in, illustration here. So this is high temperature, and we have some idealized temperature profile, right? Temperature is decreasing with height in the atmosphere. And I want you to recall that when you have this air parcel that goes up, you remember the air parcel goes up, pressure drops, the air parcel expands, it gets cold, and we have condensation of water vapor. And when water vapor condense, they release latent heat into the atmosphere, okay? So if we now gonna warm the planet, like emitting greenhouse gases, so we're going to shift this line to the right, right? And we move to higher temperatures. But because if you have a warmer atmosphere, it could hold more water vapor. So when you condense them at upper levels, the air parcel goes up. Now it holds more water vapor. It condenses, so you're going to have more latent heat release. So you're going to have additional warming at upper levels relative to lower levels. So not only you're pushing that to the right, but you're pushing more at upper levels because of this excessive latent heat that you have, because you hold more water vapor in the atmosphere. So when you do that, you're warming the fluid more than the fluid below. So you're stabilizing your atmosphere, right? You're warming above more than below. You're stabilizing your fluid. And this is why you get a weakening when you increase greenhouse gases, because you're stabilizing your atmosphere. In contrast, when you cool, like natural agents did in previous centuries, not only that you push this to the left, but you cool more at higher levels, again from the same argument, that you're going to have less latent heat release at upper levels. So it's going to add more cooling here. But this time you cool more a fluid above another one, so you're actually destabilizing the atmosphere, and this is why you get an intensification of the circulation. Okay? And as a final plot, I just want to show you how these look like. So this is the temperature changes plotted in pressure and latitude. Okay, so height and latitude. This is how it changed over the last millennium from the models, and this is how it's expected to change by the end of the 21st century. Red colors are regions of warming and blue of cooling. And I want you to focus on the tropics. So in the last millennium, we are cooling more at high levels, than lower levels, right? So we're destabilizing the atmosphere. And this is why we get more of this intensification of the circulation. By the end of the 21st century, we are warming more here than here, so we are stabilizing our column. And this is why we get less intensification. We have a weakening of the circulation. So this is one explanation for these differences. Okay, so I'll summarize. In the first part, I'll show you that we derived the relationship between the Hadisel strength and sea level pressure measurements, and we used it to show that circulation has been weakening in recent decades. We were able to attribute this to human emissions. Then we used these historic changes to constrain model projection, and we show that the circulation is projected to undergo a much larger weakening compared to current predictions, which yielded more than a doubling of subtropical precipitation increase relative to current predictions. And finally, I show you that it seems that this weakening is unprecedented because natural forcing agent seems to intensify the circulation, and human activity kind of reverse this multi-century intensification of the flow. That's it. Thanks.
Thank you very much. A lot really, and I open for questions.
Go back to this one. I want to know if how will it affect the rainfall?
Sorry?
How will the temperature changes affect the
Rainfall.
Yeah.
The rainfall?
Yeah.
So basically, rainfall is affected by, if I go back to the, right, rainfall changes would be affected by a series of mechanisms. One is related to how the circulation would change.
Yeah.
The other would be related to how much humidity you add to the atmosphere.
Yeah.
right? This would be just following Claudius Calperon. You're warming your atmosphere, then the atmosphere could hold more water vapor, basically. And it would be affected by, this is another type of the circulation, just like storms and stuff like that, like perturbations that we have in the atmosphere, and how much evaporation you have going to have from the surface. So the warming pattern itself, I would say, the warming itself is going on here. So you warm the atmosphere, you're going to have more water vapor in the atmosphere, so you get more precipitation, right? The pattern itself would be affected much by what the circulation is going to do. So you have, as you said, we have more warming at high levels than lower levels. It could stabilize your atmosphere, and as a result, that would act to reduce, for example, precipitation here in the deep tropics. So it really depends on how each one of these variables would respond to your warming or warming patterns, I would say. But in general, precipitation increase because you just have a lot of more water vapor in the atmosphere.
But continuing the same question, you cut this diagram below at 40 degrees. I just wonder if you could continue it until 60, what you expect.
So
you will have the second, not the hardest second, the other cell.
So beyond that point, you're going to have those mid-latitude perturbations, storms, and so on that contribute to precipitation, right? For example, in Europe and North America, and also if you go to the south, it's mostly storms, winter storms that result in most of the precipitation. So this term would be much more important than this term, for example. That would be very small.
Again, which one is that one?
This is just the mean Halley circulation.
Yeah.
Or the Ferrel cell would be the next one.
Yeah.
That is what we call deviation from a mean. So storms, any perturbation that you have in the atmosphere, heat waves, whatever, those goes in here. And I would expect that this would be much more important at mid-latitudes because the precipitation is driven by storms in the mid-latitude. It's not driven by the mean zonal kind of flow.
So eventually what you're saying that general-wise, you will have more precipitation point.
Yeah, just because this term is mostly increasing precipitation everywhere.
Even in 90, actually.
You would expect, yeah, almost
when you go to
everywhere. But
90.
then if you get those, for example, you can get those terms if in specific regions they could have some influence, like here in the subtropics, then you will see that. But most of the time, I would expect just to have an increase in precipitation with temperature.
In your projection models, do you take different scenarios for different carbon emissions?
So I use we use here the SSP 8.5 scenario, one of the scenarios that the UN gives. But this, you can do it for a lower emission scenario, 3.7, we did it as well. You get more or less the similar results. Everything will be shifted, it will be weaker, but in terms of percentage-wise changes, it will be the same.
And this is, so this is the reversibility of it is on timescales of hundreds of years.
So if we will take CO2 from the atmosphere, so for the Halley circulation, I don't remember. We have some experience when we do the reversibility for storm tracks, which takes centuries. Some of them are really persistent because because of the ocean.
Yeah,
The ocean, it takes so much time to cool the ocean back because of the large heat capacity and the very slow circulation in the ocean. So it takes centuries. It's really asymmetric. You can make very quick changes in the system, but if you want to bring them back, it could take you centuries because of the ocean. For the circulation, I don't remember. I can take a look.
no, but the timescale is.
Timescale is centuries, should be. Yeah.
Said that it had to do with land mass and we're kind of losing land mass at the poles.
Why we're losing land mass?
Melting ice, losing land mass, not literal land, friction based, I guess.
You have more albedo.
I'm not sure about the.
Where, yeah, more radiation, more insulation.
I'm not sure how the ferrite cells are changing in the future. I don't think many people looked at the ferrite cells. Even polar. I don't think anyone looking also. When it comes to the mid-latitude circulation, people mostly look at storm tracks and stuff like that, less of the mean flow. Not sure.
Well, you will have the albedo playing a very big game over there, I guess, right?
Yes, circulation in those latitudes are also they're driven by fluxes, like heat fluxes and so on. So it really depends on temperature gradients, stuff like that. So I guess it should weaken, but I never looked at those. So
More questions? Okay.
great, thanks.
Thank you very much.